My name is Alison Roden, and thank you guys for coming today. I wanted to just give a real sort of brief introduction to an area of math that uses finite fields, uses it in a way that we need it all the time to send information, and information when it's traveling across channels can be altered, right? There's no perfect channel. And so you send information over the computer, we interact with satellites, data is transmitted, data on a CD, right, can be corrupted. And so what you want to do is to have a way, if there is an error, to be able to identify that an error has occurred, and even better, to fix it. And so that's the idea behind coding theory, is that when we send data, we send a little extra information that helps us identify when it has been corrupted and fix it if possible. Okay? So the codes that we're going to look at are codes that are going to have make the following assumptions about them. So we're going to assume that our data is binary. So we're sending zeros and ones. We're going to assume that our channel is symmetric. Which means that when we send a digit, a bit, it's equally likely to be corrupted if it's a 0 or a 1. Right? So there's no preference. And we're going to assume also that each bit is independent, meaning that every bit is equally likely to be corrupted, and if one bit is corrupted, the next bit is as likely to be corrupted or not corrupted as if the previous one had not been. So independence of the possibility of being messed up. Is that clear? Now there are codes in which this is not going to be an assumption, because it is in fact realistic that if you have some distortion, there might be distortion nearby, right? Especially if you think about a scratch CD or a dirty CD, right? Where there's messed up, there's going to be other things messed up. Or you think about, transmitting from a satellite. If there's a solar burst, right? There's going to be a lot of things messed up in some interval. But we're not going to deal with that. We're going to say every error, every bit is independent. And then finally, we're going to send our information in blocks of bits that are all of equal length. So messages are transmitted in blocks. So whatever our message is, we're going to split it up into blocks. We're going to send the blocks one at a time. Okay? So to be very, very simple, let's assume that our blocks are length 2. So blocks of length 2 well, there are only 4 possible blocks we could have. We could send 0, 0, we could send 0, 1, 1, 0, or 1, 1. Right? Now, if we don't do any error correction or any coding of this, and we just sent these blocks, suppose I send 0, 1 across my noisy channel, and 1, 1 is received. Well, the person on the other end has no way to know that that was not what I sent, right? Because it's one of the 4 things I could send. And I have no way to, unless he says, hey, did you send 1, 1? And I say, no, I sent 0, 1. He's not going to know that that's not what I sent. So what we can do is we can add a little extra information. So instead of sending 1, 0, I'm going to send 1 extra digit. So this is a very simple code. It's called a parity check digit code. And what I'm going to do is I'm going to take each of these and I'm going to add one digit that's going to make the number of ones even. So 0, 0 is going to be encoded as 0, 0, 0, whereas 0, 1 will be encoded as 0, 1, 1. So we have two ones. 1, 0 is encoded as 1, 0, 1, and 1, 1 is encoded as 1, 1, 0. And this is what we call our code. So these are the messages we could send, and this is the code. So when I send 0, 0, I really send 0, 0, 0, right? Or actually, let me do the same thing I did here. I send 0, 1. I send 0, 1, 1. And suppose the same error occurred. That first bit was flipped. And so what is received is 1, 1, 1. Well, now, that's not a code word. I could not have sent that. So the person receiving it knows that an error occurred. Right? Does that make sense? If what I receive is not amongst the codes, there was an error. So this is not a code word. All right, so we've detected an error. And I look at the things, again, I'm the recipient. I see the 1, 1, 1. I know there's a mistake. And I look at this and say, can I deduce what the sender really meant to send from this information? Well, it could have been this, right? There's one bit that was flipped. Or it could have been this. There's also one bit difference. And there's one bit difference here. So it's not clear at all if either any one of these three was the one that sent. We're pretty sure it wasn't 0, 0, right? Because that would require 3 bits to be wrong to get that. And so, while I'm pretty sure you didn't send me 0, 0, I really can't distinguish between these three. So this has, I have detected an error, but I am not able to correct it with any kind of confidence, right? So what I can do is a different code. This next code is called a repetition code. My repetition code, I just take the word that I want to send and I repeat it 3 times. So I have the same messages possible, but now I'm encoding this as 0, 0, 0, 0. This one is 0, 1, 0, 1, 1, 0, 1, 0, and 1, 1, 1, 1. Right, so this is my 0, 0, 0, 1. That's how I'm encoding them. Again, this is my code. It's a different code than my previous one. Again, suppose that I want to send 0, 1, which I'm encoding it as 0, 1, 0, 1, 0, 1, right? And the same error occurred. First bit is flipped. I receive 1, 1, 0, 1, 0, 1. Right? Again, I know that there's an error because I was not supposed to see this different from those two. Now I look at my code and I ask, can I figure out what should have been sent? If this was sent, there are 4 errors. Not very likely. If this was sent, there is just 1, right? If this was sent, few. If this was sent, 2, right? Now, if the probability of an error is really small, it's still really unlikely that there are 2. It's much more likely that there was just 1 error, right? If the probability of the flipping is bigger than 1/2, then forget it, right? Your channel is just too noisy. But if it's small, say like in the order of probability of an error is maybe 10 to the minus 8, right? The probability of 2 errors is roughly 10 to the minus 16. It's not going to happen very often. So here I can say, well, look, these two guys are the same and that one's different. It's probably that this is where the error occurred, and it's probably here. It should have been a 0. So this code has the ability not only to detect the error, but if it's just a 1-bit error, it will be corrected. Right? Now, what is the cost of that? Over here, we took our 2-digit messages and we made them 3 digits. Here, we took our 2-digit messages, we made them 6 digits. We tripled the size of our message, right? Which means we can only send a third as much information over the same channel. So that's the downside. The upside is that I can correct a message. The downside is that I have what's called a very bad rate. Right? I look at the length of my message divided by the length of what I send, and that ratio is the rate. We like the rate to be close to 1, so it's efficient. But we also would like to be able to, here, if we receive this and we detect it but can't correct, we have to ask for resubmission, which is also expensive. Right? Here, we wouldn't have to ask for resubmission, but we're losing in terms of how much we can send. Does that make sense? Questions? So, now first of all, the other thing I want to mention is that if I have longer words, which you will, like no one sends two-digit messages, I can do the same thing. Even if I had a block of size n, I could add that 1 extra digit, make all an even number of ones. And I could, however big it was, I could repeat it and get my repetition code. The right here will always be 1/3. The right here, as my block length increases, is getting closer and closer to 1. Okay? All right, so when we're dealing with realistic codes, which are bigger than this, we can't list all our code words. Right? So we have to have some way of saying, okay, how am I encoding this? And when I receive it, is it amongst my code words? Can I detect the error? And so for that, what we want is more structure in our code than just having a list. So then we get to a type of code called linear codes. So these codes here, I took a set of words of a given length. So if and here I need to back up a little bit. Is everybody familiar with integers mod 2? These are 0, 1, addition and multiplication mod 2, right? This forms a field. Any questions? Basically, I can add, I can multiply, I have additive inverses, multiplicative inverses, distributive law, associative law, commutative law for both operations. I'm going to call it F. Now I can look at a vector space over this field. So a vector space, let's call it Fn is an n-dimensional vector space over that field F. Now we can do coding theory over larger finite fields. We're going to stick to Z mod 2. This is an n-dimensional vector space over F. What are they? They're just simply, so they have B1, or B1 for bits. There's a bit 1, bit 2, bit n, right? That's a vector in Fn. Over here, so here I just put the digits right next to each other instead of listing them in ordered tuple. Right? And generally that's what we're going to do. So this would, if I look at, say, 0, 1, 1, 0, 0 in F5, I don't really want to write it with all the commas. I'm just going to say that's 0, 1, 0. Right? So the words that I'm sending and the words that I'm encoding, the message and the encoded message are going to be subspaces of this vector space, or subsets in general. For linear codes, they're subspaces. So a code is a linear code. Call it code C. Is a linear code if and only if C is a subspace of Fn. So C is contained in Fn. In general, we say a code is just a subset. If it has an extra structure, it's a subspace, we call it a linear code. All right? Everybody know what subspaces are? Now, in general, over an arbitrary field, to be a subspace, your set has to be closed under addition and under scalar multiplication. But our scalars here are either 0 and 1, right? So scalar multiplication is not so interesting. You either 0 it out or you multiply by 1, nothing changes. So we could simplify this over Z mod 2 is C is a linear code. Over Z mod 2, if and only if C is closed under addition. Okay? And addition is bitwise, right? And 1 plus 1 is 0. Right? So those are linear codes. Now, both of these, the parity check code, parity check digit code, and the repetition code, they both turn out to be linear codes. So how do we describe a subspace? How do you describe a subspace? Basis, right? So if I want to describe C, all I have to do is tell you what the basis is. So suppose that C is a subset of Fn. F is my Z mod 2 of dimension K, right? All I need is a basis. So a basis V1 through Vk. In my code, every element in my code there must be some elements of Z mod 2, alpha 1 through alpha k, such that W is that linear combination. Right? That's what it means. The code is the span of this. Now, of course, my alpha i's are all zeros or what? So what I can think about is I can say, well, I can think about obtaining W by taking a 1 by k matrix with those coefficients and multiplying it by the matrix here, where I take my basis vectors and I just put them in as the rows of this matrix. So first row is V1, second row is V2, down to Vk. I'm going to call this matrix G. Please call my generating matrix for the code. G is going to be, well, I'm going to have k rows and n columns. So G is a k by n matrix. Right? And what W does is it just takes the first row by alpha 1 multiplies the second row by alpha 2. Right? That's what that matrix product does. Does that make sense? We're good? So I'm just taking this right here, and and writing it in the form of matrix product. So row vector times the matrix. And I can see from this that my code is the row space of G, right? The row space is all linear combinations of the rows, and that's exactly what C is. So C is the row space of G. G is the generating matrix. Right? Make sense? Now, what is the rank of G? The rank of a matrix, remember, is the number of linearly independent rows or columns, right? How many linearly independent rows or columns do we have here? What are my rows? The rows are my basis, right? They're linearly independent. So my rank is K. Right? Now, if I take a matrix and I do my elementary row operations, I do Gaussian elimination on it, what happens to the row space? Nothing. Exactly. Nothing happens to the row space. So if I took this matrix G and I did Gaussian elimination on it until I get to row reduced echelon form, then I'm going to have K pivot columns, right? Which means sitting in this matrix here, I see a K by K identity matrix. And all I have to do, if I want that K by K identity matrix to come first, is permute some of my columns. Right? So if I row reduce G and I permute some columns, so after row reducing G to reduced row echelon form, and maybe permuting some columns, which would, if I permute columns, all that's going to do is maybe permute the digits of my word, but it doesn't change the word in a substantial way. Maybe permuting some college, we can put G in the form it's going to be a K by K identity matrix, right? And then some matrix over here, P. I don't know what P is, but I do know the size of P. P is going to be K rows, and G had n columns, right? And K of them were taken up by my identity matrix, so n minus K columns. When I put G in this form, notice what happens. I take an arbitrary word, that's my message. That's the message I want to send, right? And multiply it by G. What comes out the other end? What's the first entry of this matrix product? Multiply first row times first column, right? What's your first column?
0, 0, 0.
1, and then lots of zeros, right? What's that matrix product going to be? Alpha 1, right? Second one's going to be alpha 2. way to alpha k, right? And then I'm going to get some b1, b2, up to bn minus k. So what's nice about this is what's called is a systematic code. Because the message I'm sending appears the first k digits of the code word, right? As in the codes that we saw earlier. The first k digits, these are the information digits. And these are my error correction detection. These are called the parity digits, or parity check digits. Right? That's the extra stuff that helps me to determine if what I received is what was up. Okay? So, for example, for our parity check digit code, our generating matrix is going to be, it's a 2 by 2 identity because we're sending words at length 2. And then we add the check digit, right? If I take a message alpha 1, alpha 2 times this, what I get is alpha 1, alpha 2, alpha 1 plus alpha 2. Right? That's what comes out. And notice that whatever these are, this is going to have an even number of ones. How do you know that? How do I know that this is guaranteed? No matter, you tell me any alpha 1, any alpha 2, I will guarantee you that this message here has an even number of ones.
Because it's alpha 1 plus alpha 1.
Right, if I add up all the digits, I get 2 alpha 1 plus 2 alpha 2, which is 0. Right? The only way to get 0 is if I have an even number of ones. So that's my parity check digit. There. That's my generating matrix for that parity check code. If I had more digits, I would do the same thing. If I was sending a message with 4, I would have a 4 by 4 matrix, identity matrix, and ones in my next column. Right? Those are my parity check. What about the repetition code? Again, I'm sending 2-digit blocks, and now what's going to come after? See it, my repeating? The same. 2 more identity matrices, right? And then alpha 1, alpha 2 is sent as alpha 1, alpha 2, alpha 1, alpha 2, alpha 1, alpha 2. Okay? Those are my, and if I wanted a repetition code, or larger blocks, right? I want to send repetition code with n blocks, I would have 3 n by n identity matrices side by side. All right, any questions so far? We're good? All right. Now, again, if we have a more realistic code than the ones that we've been looking at, I want to be able to detect without having to search, right? I may have a lot of code words, and I get my error. I don't want to have to do a search through all the code words to see, is this a code word or is it not? So the idea is that because we put in this structure, we have an easy way of error detection. And that is to do the following. I'm going to introduce a new matrix. I'm going to define, so suppose that C is a linear code with generating matrix G, and we put it in the systematic form, looks like this. I'm going to define a new matrix, H, and H is going to have the following form. I'm going to put P here, And then I'm going to fill in down here with an n minus k by n minus k identity matrix. All right, so let's look at H. H is going to be, I'm going to have n rows, right? Because P had k rows, and now I have n minus k more rows. So it's an n by n minus k matrix. Now, let me just add here that because we're working over Z mod 2, I see the same matrix P. In general, it's going to be minus P if we're over a more general field. But over Z mod 2, minus 1 is 1, right? So we can just say P. What is special about H this is a property of H, is that if I multiply G by H, my generating matrix times this matrix H, it's going to be a zero matrix. It's going to be a K by n minus K zero matrix. And you just check it. Take the ith row of G and you dot it with the jth column of H. That gives you the ijth column of the product. And what you're going to find is this is Pij plus Pij, which is 0. Right? More generally, it would be Pij minus Pij if this was H had my minus P, but for us it's 0. Because of the way it's set up. So what that means is that if I have a code word is of the form B times G, right? Say W. If I then multiply by H, I get 0. So that means that W is in the left null space of H. Every code word is in the left null space of H. Now, what is the rank of H?
We said minus k?
What's that?
No, it is a minus k.
The rank? There are at least n minus k independent rows, right? N minus k. And that means that the dimension of the left null space is k, which is the dimension of C, right? That means that the set of code words are a k-dimensional subspace of a k-dimensional space. It is the left null space. So C is the left null space of H. Which means that instead of describing C by my generating matrix, I could have equally well described it by its, this is called the parity check matrix. H is called the parity check matrix. That make sense? So I take any matrix, n by n minus k matrix, in this form. I define my code to be its left null space. I have defined the code, right? Alternatively, I start with my generating matrix, and I define it to be the image, right, under block multiplication. What is the parity check matrix? For the parity check digit code. I had G. Right? That's my P. So the parity check matrix, I start by putting P here, and then I fill in with the identity matrix. What's the identity matrix here? Only room for one digit, right? So 1 by 1 identity matrix is this. Right? I take my word, which I add in parity check digit. If I add up all the digits, I'm going to get 0. It's a code word. And if I don't get 0, it's not a code word. Right? For the repetition code, G was so what's H going to be? That's my P. And what do I have to fill in down here?
4 by 4 identity matrix.
4 by 4 identity. Right. I take any code word and multiply by this, and notice I'm adding up the corresponding positions, right? If it's a code word, I'll get 0. If it's not a code word, I'll get something other than 0. Okay? So that's my parity check matrix. So that's how I do my error detection. Error detection. So the sender sends a word, encoded word, right? W sent as encoded. Receiver computes. WH. Two things can happen. You get 0, no error. Right? Let's start with this. Non-zero. It means there is an error. W, not a code word. You know there's an error. Error detected. But if WH is 0, do you know that there was no error? No, you don't. You know you received a code word, right? Code word received. Probably there's no error, but there still could be. Now, the type of coding that we're doing is called maximum likelihood decoding. You're going to, if you receive a word that's not a code word, you're going to take it to be the code word in which there were the fewest number of digits changed to get to the word you received. Right? And so in order for you to see no error detected, but actually there was an error, you have to be able to get from one code word to another code word. Right? So the number of digits that are different between code words is a really important measure of how likely it is that you did not detect an error. Does that make sense? So we're going going to define something called the Hamming distance. If I have two words, W and V, so W and V are in my ambient space, right? Not necessarily code words, but just words that could have been sent. I'm going to define that to be the number of positions in which they differ. Right? That's how many bits I would have to flip to get from W to V. Right? This turns out to be a real distance. It satisfies the triangle inequality in particular. Now, there's a related measure, which is the weight of W, and that's the number of ones in my word W. Now, because we're dealing with linear codes, which are closed under addition, then I can say that for a linear code, the distance between W and V is the weight of W plus V. Linear code over Z2. Right? Otherwise, it would be W minus V. Does that make sense? If they differ, if they're the same, any digits are the same, when I add them, I'm getting a 0. The only way I can get a 1 is if they're different. So then I can define the distance of a code to be the minimum weight of a non-zero code word. So it's the minimum of the weight of C such that C is a code word and C is not 0. Obviously, the weight of 0 is 0. Right? So I take my non-zero code word and I look at the minimum weight. So let's look at the two codes we have so far. So our parity check code, which was this one. What is the distance of this code? What's the weight of this vector? 2, 2, 2. Those are my non-zero vectors. They all have weight 2. The minimum is 2. Distance is 2. And what that tells you is that if I send this code word and you receive this code word, there had to have been 2 errors. At least 2 errors to get from one code word to another code word. What about my repetition code? So my repetition code was this one. What is the distance of this code? 3. So it's less likely for me to get one code word which is not the code word sent for the repetition code than for the parity check code. We like a big distance. We like a large distance on our codes. So now, this is a really important property of the distance. Call it theorem. If the distance of my code is D, then I'm guaranteed to detect any D minus 1 errors. Right? Because if I have D minus 1 or fewer errors, I will detect those errors. And if D is in the form 2t plus 1, or let's say D is greater than or equal to, a little bit broader, D is greater than or equal to that, then any T errors can be corrected. And here's the idea there. I think about my code words sitting out in space. And I'm going to create a neighborhood of each of those. I'm going to put a ball around them whose radius is at most t. So it's called a Hamming ball. As you see, Hamming had a lot to do with this. Hamming ball. Around C, it's the set of words such that the distance between W and C is less than or equal to T. All those words that have fewer T or fewer errors if C was what was sent. Right? Now, if I look at this is radius T, this is radius T, right? This has radius T, but my distance is 2T plus 1, right? So if I have sent a word that contains T errors, it is going to be in exactly one of those Hamming balls, which means it's going to be corrected to the correct word. If I have more than T errors, I can't guarantee it, right? But T or fewer errors, I will correct it. So for my repetition code, I can correct any single digit error, right? For my parity check code, not good enough, right? I can correct 0 errors, as we observed. Does that make sense? So the big idea with encoding theory is to somehow manage to have a large distance, but a small rate. Right? We want K over N. K is the size of the message we're sending. N is the length of the encoded message. We want K over N to be close to 1. We want D to be big. And unfortunately, those two things don't go well together. Right? You kind of have to play one against the other. There's some bounds relating to K and N that give you, upper and lower bounds for a particular D on what K and N can do. Okay? So I think I have time to